We currently treat artificial intelligence as a top-down engineering problem. The objective is to build a uniform architecture and use massive datasets to force a specific type of intelligence into the system. Biological intelligence operates on a different logic. It is not assembled from discrete parts. It is grown, allowing organic material to autonomously expand and wire itself together. This is the concept of algorithmic growth. In a brain, the physical sequence of development is not just a precursor to function, it is the foundational code. Because biological growth follows these evolutionary rules, the brain never starts as a blank slate. Its physical construction acts as a massive inherited pre-training phase. This creates a structural clash. We are trying to merge rigid, top-down engineering with bottom-up biology that has been grown over millions of years. If we want to achieve true general intelligence or build successful brain-computer interfaces, we have to resolve this friction between the engineered and the grown. We can see the efficiency of biological growth by looking at the connectomics of the Drosophila, or common fruit fly. With roughly 100,000 neurons, the fly can execute hundreds of complex behavioral tasks simultaneously, from flight stabilization to visual tracking. We might assume a network of this size functions as a uniform, randomized mesh of connections, but the internal reality is far more organized. The fly's brain is strictly modular. Instead of an even grid, it consists of specific interconnected subnetworks that perform highly specialized tasks. These subnets are wired to govern specific functions long before the fly ever takes its first flight. This inherited architecture stands in direct contrast to how we initialize a standard artificial neural network. When an AI model with an equivalent 100,000 parameters is created, it begins as a blank slate. Every connection is assigned an entirely random starting weight. To create intelligence from that randomness, we use brute force training, feeding the system millions of examples to slowly find patterns in the noise. Biology starts with localized modularity. AI starts with uniform randomization. While AI requires massive amounts of data to overcome its random starting state, biological intelligence derives profound efficiency directly from its physically inherited architecture. If this modular architecture isn't learned from external data, we have to look at where these precise connections actually come from. The process begins with the genetic code, a highly compressed instruction set that coordinates the beginning of life. During the molecular execution phase, cells follow these instructions to physically divide, migrate, and build the physical housing of the brain. In the axonal wiring phase, dendrites extend to form structural connections. The network is essentially locked into place before the organism ever experiences sensory input. This phase of construction is evolutionary programming. In the organic world, the physical growth of the system is the initial learning phase. AI engineering takes a significant shortcut here. To save time and processing power, computer science abstracts away this entire molecular history of development. When we discard this biological mess, we also discard the underlying logic that shaped it over eons. This engineering shortcut treats millions of years of evolutionary problem-solving as irrelevant data, choosing brute force computation over the efficiency of a grown architecture. This divide between the engineered and the grown is the central challenge for brain-computer interfaces. The current tech industry approach treats the human brain as a hardware problem, a question of maximizing data bandwidth. This has led to a push for high-density electrode arrays, designed to be inserted directly into the motor cortex. But the brain is not a hard drive. You cannot simply plug in an external device and expect an instant data download. Integration depends on Lashley's equipotentiality, the intense physical plasticity of the cortex. For the brain to use a static interface, neighboring neurons must physically rewrite their connections to interpret the artificial signals. This is a grueling metabolic process. The brain must expend vast amounts of time and energy to physically grow around the machine. It is more like the brain slowly attempting to learn how to operate a sudden third arm than it is a simple software update. BCI integration is not a seamless engineering victory. It is a biological labor, where a grown system must physically adapt to accommodate a static machine. This friction is about more than just physical wires. It changes how we process information itself. In a biological brain, every new piece of data is permanently altered by the historically grown architecture that processes it. The organic network instantly warps any incoming signal to fit its existing messy structure. This loop, where incoming data modifies and is modified by a biased biological structure, is what we call dynamic normality. Because of this inherited bias, the brain perceives reality only through its own algorithmic past. It can never be a neutral processor. Successful human-AI integration requires a reconciliation of structural history. The challenge is forcing a perfectly engineered, static system into a biological network that only derives meaning from its own evolutionary growth.